Alright, thanks for watching, and today I would like to discuss two pitfalls that happen when you want to use the fundamental theorem of line integrals. So let's try to evaluate the FTC for line integrals where f is 2y, 3x, and c is a circle of radius 2 centered at 0, 0. So as usual, let's draw a little picture. We'll see what it is. It's just a circle of radius 2 in xy. So that is C, and unless otherwise specified, it's in the counterclockwise direction. So circle of radius 2 in the counterclockwise direction. Then the next step is to check whether f is conservative. Is f conservative? In other words, do we have that pi m equals quixotic? So py is the derivative of 2y with respect to y, which is just 2. Qx, that is the derivative of 3x with respect to x, which is 3. In other words, py is not qx, which means you cannot use the fundamental theorem for line integrals to evaluate this. And because basically what this says is you cannot find an antiderivative of f. There is no function little f such that this is the gradient of little f. Well, what could you do in this case? Since the FTC for line integral doesn't work, you have to do it directly. Or we'll see soon there's something called Green's theorem that works for those kind of line integrals. But at this step, just do it directly using parametrizations. Then just parameterize again. Part 2 again. Parameterize c, so x of t is 2 cosine of t, y of t, it's 2 sine of t, and t is from 0 to 2 pi. Then the line integral over c of f dotted with dr, that becomes the integral from 0 to 2 pi of 2y, which is 2 times 2 sine of t, so 4 sine of t, 3x, which becomes 6 cosine of t, dotted with the derivative, so minus 2 sine of t, and 2 cosine of t, dt. That's what we have. Okay, supposed to be here, but I don't want to ruin my pretty picture. And then what we get is it's the integral from 0 to 2 pi of, so 4 times minus 2, so minus 8 sine squared of t plus 12 cosine squared of t dt. Sure, you could simplify this using, in fact, let's do it. It's simplified using the identity cosine squared is 1 minus sine squared. So integral from 0 to 2 pi minus 8 sine squared of t plus 12 times 1 minus sine squared of t. So plus 12 minus 12 sine squared of t dt. And then what this gives you is the following. So basically, minus 20, so integral from 0 to 2 pi of minus 20 sine squared of t plus 12 dt. And then this one you just evaluate. So that becomes the integral from 0 to 2 pi of minus 20 1/2 minus 1/2 cosine of 2t. And then plus 12 times the integral from 0 to 2 pi, that becomes 12 times 2 pi, so 24 pi. So this is with respect to dt, and then you're adding 24 pi to your answer. And then this, I think you can simplify. Integral from 0 to 2 pi of minus 10 plus 10 cosine of 2t dt plus 24 pi easy example, unknowing integral. And then you evaluate that, so integral of minus 10t and then plus 10 sine of 2t divided by 2. Because you see, when you differentiate sine of 2t, you get cosine of 2t times 2. So we have to divide by 2 to make this work. Again, from 0 to 2 pi plus 24 pi. And then I think what we get is just minus 20 pi plus, so this is nice, so this becomes 5 sine of 4 pi, which is 0, minus 5 sine of 0, which is 0. So in the end, we get minus 20 pi plus 0 plus 24 pi. And in the end, I believe the answer is just 4 pi. Let me just check. Yes, indeed, that is correct. So that's one thing. The first pitfall is, if the vector field is not conservative, you cannot use the FTC, so we have to resort to other techniques like calculating it directly, or we'll see later, Green's theorem actually also makes this much easier than here. That's the first pitfall. The next one isn't really a pitfall, but basically it's a problem where there's an easy way to do it and a hard way. How about we still take, again, C is just the same circle, and this time f of xy becomes, well, let's choose something conservative this time, 2xy and then x squared. And the idea is, let's calculate the integral of f dotted with dr. So again, the picture is the same. So we have a circle of radius to counterclockwise. Now, check f is conservative. Well, let's calculate py. So 2xy, y, that's 2x. qx, that is x squared with respect to x. And that's 2x. So indeed, pi m is quixotic. So it is conservative. Okay. Now, there are two ways now of doing this. And just be careful, it only works more or less for curves like this that are closed. You could either find an antiderivative, apply the FTC for line integrals, and feel very dumb at the end. Or there's an easier way of doing this. Notice C is a closed curve because the starting point is the ending point. C is closed. And F is conservative. And remember, there was this really nice property about conservative vector fields, which is in another video that's called path independence. And the nice thing is, if F is a conservative vector field and C is closed, then automatically the line integral of F over the curve C is automatically 0. And that's in some sense because the vector field doesn't rotate around C, so in some sense the general contribution of F over C is just 0. Again, you could have done this using the FTC for line integrals. I think you would have found that an antiderivative is x squared y, and then you would have calculated f of the endpoint minus f of the starting point. But since the start equals to the end, you would get 0. So that's a second pitfall I wanted to talk about. The first one is if f is not conservative, for now just do it directly. If f is conservative and the curve C is closed, then it's automatically 0. But beware, C has to be closed. If I gave you the same example over something where start is not the end, it's not necessarily 0. So just beware. It's like the third little pitfall if you want. And so that's it. So if you like this and you want to see more math, please make sure to subscribe to my channel. Thank you very much.